Hi, this is homework 10 question 1. So we are asked to list the definitions and simple properties of various stochastic processes. Firstly, there's the Poisson counting process. The Poisson counting process, for this, the properties I have written below. So some of them are like the number of points ti in the interval t1 to t2 is a Poisson random variable with the parameter lambda t. So it's just like we have studied in for Poisson random variables. And here t1, t2, t3, t4, if these two are non-overlapping intervals, then they are independent, and this is usually the graph of xt, the stochastic process in relation to time. As you can see, and basically xt is also a linear function of time. So a very common example is the longer you wait, the more chances of getting a bus. So that is basically a real life example of a Poisson counting process. And the autocorrelation is a property of independent increments. This is also a property. So next we come to the Poisson increment process. As you can see, I've listed the the definition. Xt is a Poisson process, so yt is defined as this. This is called Poisson increment process. Listed out various properties, and here you can see that the autocorrelation function is something like this, as you can see, and it is a triangle with area lambda and is independent of epsilon. And when epsilon tends to 0, as you can see, when it tends to 0, then the whole autocorrelation becomes an impulse with area lambda, right? So Poisson increment helps us define Poisson impulse processes. Now coming to Poisson impulse process, for this basically you have taken the derivative of a Poisson stochastic process. As you can see, I've listed out the basic properties and definitions and things like that. This is the usual graph. These are impulses of the Poisson process. There is derivative. So basically, if you take derivatives, since Poisson process is almost like a step function, it comes out to be like impulses. Yeah. And so if we consider this Poisson impulse process zt minus lambda, that has some interesting properties. It is like white noise, and it can be represented like this. So it is the output of a linear time variant system with the impulse response ht, and input is the output is the impulse response ht, and input is Poisson impulse process, obviously. So for semi-random telegraph system signal, we know that it starts from +1, and for random telegraph signal it can start from +1 or -1. So xt, the telegraph signal, it is defined based on Poisson points, and it's 1 when k is even in 0 to t, and -1 when k is odd between 0 to t, right? And you can say it is also like Poisson process. It is like the number of points, n t1 t2 is the number of points in the interval t1 t2 and all that. So the first order probability masses I have just listed here. And since the process is semi-random, as I told you, it starts with always +1. Hence p of xt equal to 1 is not half, rather it is a bit more than half, because obviously it starts with 1. So as t tends to infinity, xt equal to 1 becomes 1, and expectation tends to 0. When t1 t2 are very far away, that is T1 is much larger than T2 or T2 is much larger than T1 and T1 minus T2 tends to infinity, then the autocorrelation tends to 0. This makes sense because basically this means that T1, T2 are very far away and XT1 and XT2 are not correlated. That's why, because they are far away. So as I said, in random telegraph signal, it starts with either a 1 or a -1 and we represent this by the variable a. So probability of a equal to -1 or a equal to 1 is half. It can take either value in the starting, and then xt is the same as semi-random telegraph signal. Yeah, first order probability masses I have listed, and one interesting fact is yt, the for random telegraph signal, may be strict and stationary as expectation of yt is 0 and yt equal to 0 and probability of yt equal to 1, which is equal to probability of yt equal to -1 is half basically. So random walk is like n tosses of a fair coin and getting k heads. So again, I've listed the first order probability masses, the expected value, autocorrelation, autocovariance, etc. So here we can see that as n tends to infinity, we have a Gaussian density, and as the autocorrelation contains minimum of T1, T2, this comes from independent increments that we have seen earlier, that I've explained earlier as well. So Wiener process, this is commonly called Brownian motion. So here you can see that Wt is a Wiener process when limit xt t tends to capital T tends to 0 and n tends to infinity. First order density is given, autocorrelation is given. So W0 is equal to 0 with probability 1. So it has a lot of properties. I have listed 2 here. That is when Wt has independent increments. As you can see, when this is the case, then it is independent of variance, and W has Gaussian. When it has Gaussian increments, then this is basically density, normal density with 0 mean and variance u.